Hello, everyone. I'm Dr. Owen Kenway. I work at University College London, which is obviously the best university in the world. Um, but more specifically, I think we describe ourselves as London's international university. We're a reasonably large research-focused university in central London. We have about 10,000 staff and 50,000 students. And for the last 15 years of my life, I've been working supporting the high-performance computing systems that we provide to researchers. And these are systems used for a wide variety of applications from sort of, frontiers of theoretical physics work all the way through biosciences and chemistry, all the way down to we have, thanks to the revolution in large language models, things like the Faculty of Laws doing stuff where they analyze ancient legal texts. Um, and so I'm part of the team that looks after the central HPC services. And my real focus is looking at technologies we might put into production for our researchers tomorrow, right? And I'm here to talk to you about LinuxONE and specifically doing machine learning on the LinuxONE system. Just calling back to Frank's talk, I am actually logged in here. Thanks to some hard work, I think, actually by IBM, you can now run LLM inferencing on the LinuxONE. So this is a tiny VM with 2 processors on our LinuxONE running the IBM Granite model. So it's not quite up there with running on like a large GPU, but it's almost usable. It's doing pretty well for a CPU. So LinuxONE. What do we have at UCL? Well, I've been interested in looking at the performance of mainframe for one of our particular use cases. Specifically, a lot of our HPC systems are very focused on doing floating point math very well, right? If you're doing physics or chemistry, you're evaluating forces and doing integrations, you need lots of floating point performance. But there's another big user of our systems, which is biosciences, and they do a lot of workloads which actually look very much like the kind of workloads a mainframe might be good at, right? They are based around very high I/O. You're comparing gene sequences, which are very large files, and you're doing pattern matching and searching to connect up the ends of those gene sequences. And so back, I'm going to say about 10 years ago, I started casting about to work out how we could serve these scientists better, right? Our systems were very focused on floating point, not so much on I/O. And I sort of stumbled across the mainframe as an architecture which is very based around I/O, right? It's based around handling trillions of transactions every day, doing so reliably. But at the time, IBM's offerings were very much not suitable for us. They have this they were designed to fit in their own special racks. They had a whole lot of, they ran ZOS, which for us was not really a starter. We were very much a Linux shop. But there was this sort of side platform they had called LinuxONE. And so I kept my eyes on it. And shortly after the pandemic, IBM announced this thing called the LinuxONE Rockhopper at the time, which was the kind of the first model that you could buy to fit in a normal rack. And we have a budget at UCL for doing research and development. And thanks to some hard work with the local IBM representatives here in the UK and with our resellers Logicalis, we were able to procure the first of the LinuxONE Express 4. So that is the now previous generation of systems, but the first one in the UK to be installed here at UCL. And it's kind of by our standards a tiny machine. It's got 4 IFLs, which are analogous in my head to processors. It's got 384 gigabytes of RAM. It's attached to 115 terabytes of storage. And really, we're using it for doing kind of 3 real strands of work, right? But first of all, what is this machine? It's a very strange machine. It's a 64-bit machine that runs Linux, but it's not an architecture you will stumble into, without talking to a mainframe. It's not x86-64 like most of the systems. It's not ARM like a Raspberry Pi or like Grace Hopper on the new systems from NVIDIA, or even Power, which we had stumbled into in our previous career because there was a period of time where IBM were very big in the high-performance computing market with Power. So really the first test we did on the system was, can we even get software to work on it? And there's a very common packaging system for scientific applications called SPAC. And the answer is yes, you can just compile software and it works, which is kind of what you would hope. A lot of scientific software is designed to cope with weirdnesses like Big Endian because it dates back to the days when Power and Alpha and other architectures were common. Um, so the answer is yes, you can just install scientific software on it. Um, so what do we have this machine for? So there are kind of three things we're looking at. One of which is we've done a lot of progress on, I'm going to talk about in this talk, which is looking at, so in order to help banks and other financial institutions deal with fraud, IBM have added a small AI accelerator into that generation of machine. And so we were interested to see if that is powerful enough to use on other workloads than fraud. Um, we're also, UCL does a lot of work with medical data, and so we're very interested in the security features that are built into the hardware on the platform. And one of the things we want to look at that we've not started yet is looking at how we can expand out our private cloud onto the system and then use the security features to protect data that we have to protect, like medical data, or we get like commercially sensitive data sets when we're doing research with companies and things like that. And of course, the final strand is the strand that originally kicked this off, which was looking at whether the platform is very good for gene sequencing. So the Z16 and now the Z17 and the LinuxONE 4 and 5 has an AI accelerator. Why does that exist? Well, it does seem a bit odd. I mean, we all have this like perception that mainframes are these massive black boxes that sit in data centers in banks, and all they do is crunch through our financial transactions. Um, but obviously, one of the problems that we have in the world today is fraud, right? I don't know what it's like in the States, but in the UK now, when you go into a bank, there's no glass counter protecting people because people don't rob banks anymore, right? They rob their customers through the internet. And so IBM have put in the current generation of systems a tiny AI accelerator, the goal being that every time you do a card transaction, there's a fraud detection inference step that happens, very low latency, right? So that it doesn't affect you, you don't notice that as a customer. This shows up on your system as the NNPA feature if you look in proc CPU info see that's available, right? Um, and IBM has a bunch of libraries that leverage the features of this accelerator, and it's called ZDNN. It's all open source. You can get it on GitHub, or you can actually, if you're running Red Hat, you can just DNF install it. It's got a series of tensor operations for machine learning with low precision float types. If I say low, it's low in my mind because in HPC we do a lot of 64-bit floating points. This tops out at 32-bit, which we would consider single precision. And you can quite happily look at the documentation and use this to write some code in C++ or C, and it will work. But AI developers don't tend to implement things at that kind of low level. They're very into using high-level frameworks like PyTorch. And there's really two ways currently that you can run PyTorch models on the platform, and we'll look at both of them. The first and the only way that was available when we got the machine initially was by a method that a lot of dedicated inference accelerator companies use, which is you train your PyTorch model on a different system, and then you export it to this format called ONNX, and then you put it through some kind of specific platform-specific compiler, and then it will run. You can run the model on your accelerator. But recently, I think in just before Christmas this year, IBM sent me a special Christmas present, which is they now support PyTorch natively on the platform as well, so you can directly run your PyTorch model. When you have your ONNX model, there's this thing called the ZDLC compiler IBM provides. You can either download the source code and build it yourself, or there's a container on IBM's container registry. And what this does is it builds a library, and then it's your job to write a wrapper application which calls that resulting library. So here we have the workflow, right? We have a training system. We train our model for however many hours, days, weeks to get an optimized model. We take that out in ONNX format. We run it through the ZDLC compiler. That gives us either a .so file, or if there's actually a version which gives you a .jar file for Java if you like Java code. and we can run that code on the IBM LinuxONE. So medical imaging, why do we care? Well, obviously, UCL does a lot of medical research. Frank mentioned before GDPR. Actually, in the UK, probably the most nasty set of regulations around data are the kind of the rules you have to sign up to get access to NHS data. So we have a National Health Service. Um, that is basically all of the medical data for people in the UK. And if you mishandle a data, so if UCL was to have a leak, that would probably result in us losing our ability to use NHS data, which would kill off entire departments, right? So you really want to, when you get your hands on NHS data through legitimate means, you really want to make sure you keep control of it. And the LinuxONE has a lot of really interesting hardware features around security, around encryption, around secure execution. Um, that would be really nice to make use of instead of sort of the current approach of layered third-party software products. So if we can, in this environment, get the performance we need for doing, for example, medical imaging, we can use this platform safely with people's medical data, right? So this work has been looking at an example data set, not of real people's data, well, not of an open data set, not of a specific person's data, which is called a MedMnist, because it sort of apes a little bit the FashionMnist and other open data sets people use for messing about with AI. But this is a really cool data set because it's not one data set, it has about 12 or 13 different data sets of 2D and 3D sets of real medical slides that have been classified. And for this work, I've been using one called PathMnist, which is a data set of colon pathology slides, which has about 90,000 training images and about 10,000 validation images and about 7,000 test images. And you can pull that down from their website, or actually they've got a nice framework so you can pip install it. And on the right here, we have one of the images, a test image, um, which, you know, if you look at the actual images themselves, they all look like this because they've got this like stain in them so that you can, so that to help show up features. So what do we do to look at this on the LinuxONE? Well, the actual file itself is about 12 gigabytes, and it's in this weird format, which is basically a stored NumPy array. So NumPy is a library for Python for doing numerics. And so what we want to do is build a training pipeline to which we can run on platforms that are not the LinuxONE. And I did that. I've gone through several iterations of this on different platforms, from GraphCore, which was another AI system that we have in UCL, all the way through to modern systems. The most recent set of models I've built have been built on, we have an AMD MI300X platform and also a NVIDIA H200 based platform. But you want to build a pipeline that whatever, regardless of what the underlying hardware is, you can run the same pipeline to do the training. And for that, I use a toolkit called PyTorch Lightning, which is a kind of high-level orchestrator for PyTorch. The second problem is that if we imagine this in like a production environment, we don't really want to force medical personnel to pass around weird NumPy formats for files. So we want to have a system that can read in real image files. And so on the inference side, we need to write the pipeline so that it reads the image and then does some transforms in memory. And this is actually quite important because if you look at the output of the compiled ONNX model, um, that's a C program, right? That's got very like strict ideas about how things should be ordered in memory. And Python, for all of its wonderfulness in being user friendly, hides a lot of that complexity away from the user. And actually, one of the really interesting bugs I had early on was Python will say that two arrays in memory that are ordered differently are the same if they are conceptually the same. And that causes all kinds of problems. And so again, that code is available in the Git repo that was on the previous slide. And you can successfully run this on the LinuxONE, right? And again, I dangerously going to do a live demonstration here. But the classifier here, that was almost instant, right? That was running a test on about 10 images. I happen to pick 10 images where it's correct all the time. But you know, it is quick enough to be used in a clinical environment. So that was using ONNX. Can we do this in PyTorch? Um, yes is the answer. And again, it's very like IBM provides a container with a modern version of PyTorch installed in it. It's missing some components. So if you're familiar with machine learning, PyTorch is not just like the base PyTorch. It's also there's this thing called Torch Vision, which does a lot of useful stuff for machine learning with images. And if you do audio, there's an audio layer as well. So you have to kind of match those exactly to the versions that are in the IBM container. But one of the really nice things is there's a lot less, because you're inside Python, you have to write a lot less code to reorganize the arrays in memory because that's all done for you. Um, so moving on, we can look at kind of the performance of this. If we remember that the use of the accelerator is batch detection of low latency fraud, right, in very small batches. So as you're doing the actual transactions, one of the things that's quite interesting about the architecture IBM have built is that it does seem to be optimized to run smaller batches, right? The graph on the right is showing as we increase the batch size, so the same total amount of it, same total number of images, it actually takes longer, which is not what you would expect from like a GPU. On a GPU, you really want to load the entire data set into GPU memory and do it all at once to get the best performance. The other interesting effect is that parallel execution of the model improves throughput. And the other thing we can do is we can compare whether that hard work we did making the ONNX model work is worth it in performance terms versus PyTorch, right? So this graph is showing the breakdown of the runtime for doing inference on the entire test set, which is about 7,000 images. And this is the same model converted into both ONNX and PyTorch. And what we see is that the green chunk of this graph here, which is the actual inference time, is much smaller on the ONNX model, right, when we are NP2 than it is on the other options. But that we waste a lot of time here in this orange chunk, which is where we're reorganizing stuff in memory. And that's super interesting, right? That implies that we can get, you know, there's a lot more performance to be had here if we can optimize this step outside of the accelerator. So we had some problems getting it working, which were not really to do with LinuxONE. They were to do with, as I said, Python and memory ordering and how it kind of hides things from you. Um, the training inference code has been very generally written so that we can move to different models. And in fact, in there, I've shown you when it was running live, I was showing you it running on a model that wasn't set up when I wrote these slides, a much larger ResNet model. Because of course, accuracy also matters. So we've been looking at really here is performance. But what we want to get is an accurate enough model, right? What is really nice for developers is that the PyTorch performance is comparable with the ONNX model. It's not like hugely slower. Um, and that's really good in terms of allowing developers to iterate quickly when developing code. The final piece really was one of the things we've learned around working with AI accelerators that are not GPUs is the software really matters. And again, calling back to Frank's talk, the thing NVIDIA have done really well is have incredibly good compilers and toolkits. And that's not common on custom accelerators. And one of the pleasing experiences of using the LinuxONE has been that those Docker containers that IBM provides do work. And they also provide GitHub repos with clear examples and clear instructions, and the lights in this building have just gone. And much of this is available as open source, so you can build upon it. So that's that. Questions, I think. Hello?
Any questions for Dr. Kenway?
Yeah.
Oh, JP.
Thank you very much for your wonderful presentation. Just a question in regard to how labor intensive was it to go through the steps that you described?
So it was just me working on it, and I think the actual development is probably a couple of days' work. Mostly the difficulty really was with with the O and the X models, thinking about how they are in real memory, right? Because you end up with although you're programming in Python, you end up with this library that is a compiled C program, right? With all of the like limitations that gives you. But I've said this was of the many accelerators we've tried, this is by far and away the least painful.
Well, thank you. That's really quite quick, several days.
That the majority of the time has been doing the training runs on the other systems.
One other question I had is for the open source GitHub stuff, you find that that's a rare resource to find as you're developing some of these language models? Like, are you seeing that it's, very accessible to have those open source, or is that something that's unique to LinuxONE and the IBM, model that you're working with?
I think what is challenging for a lot of companies is having accurate documentation. Again, calling back to the talk before, this is a very fast-moving field, right? And if your company's focus is hardware, it's very easy for the documentation you provide to people who buy your hardware to fall behind quite quickly. And actually, we saw that with, for example, GraphCore, right? They started out really strong, and then have had some challenges. And if, the quality of documentation and the fact that the tools work as advertised is really helpful.
Got it. Thank you.
And for example, the ZDNN stuff, you're not supposed to write programs in that really, but you can look at the documentation and work out how it works, and look at the code in GitHub and work out how it works. And I wrote a silly program to like estimate pi, not super quick because it's not very optimized, but you can write code in that from what's in GitHub.
Right. Yep. Absolutely.
This is more of a thank you again, more of a question for your role at ECL as to what your approach is to provide systems and tools to the researchers so they're more enterprise-like or scalable and not as if they're developing pilots or trials for each research project.
Yeah, so prior to my current role, I was head of the research computing team. And one of the things we've really pushed on has been what I would describe as cloudifying our HPC. So I don't know what backgrounds people have here, but high performance computing is this really weird field where the hardware is state of the art, and we log into a Linux shell and submit work to a batch queue like it's 1970, which is great for physicists and chemists because they've been kind of trained to think that's the way things should be. But it's quite bad, for example, for those people from laws or even like biosciences, and particularly it's bad for like AI researchers. AI researchers really expect to have interactive access to the system and do all their visualization, run notebooks or Visual Studio Code or whatever. And so what we've been moving to, talking about a bit about that piece where I hinted at that, about talking about integrating that into our private cloud, is we're moving to a setup where our HPC systems look like the cloud, right? We can deploy, if laws need some weird laws tool that they use, no one else does, we can just spin up some instances for them in that. And that's a lot more flexible, but it's a lot more pain to manage as well. So our approach has been to kind of set up that cloud infrastructure and then shift some of that installing applications and looking after applications to the departments. And I think that's bearing fruit, but we're quite early on that journey.